Good morning, my friends. Let me start off by just saying good morning, Tessa. I win that one. Unless, of course, you shouted good morning at the screen already, and in which case you probably win that one. But I'll let you decide that. Molecularity and reaction mechanisms, what we're talking about today. We started the discussion yesterday, and I'm going to finish up today. All right, let's get started. Molecularity tells us how many particles have to collide in order for a reaction to occur. For example, if something is unimolecular, that means that only one particle is banging around, and all it has to do is hit something hard enough, be it a particle of the solvent, another one of itself, the walls, whatever. Just hit something hard enough to break it apart. We typically can picture these unimolecular reactions as being decomposition, so something busting into two pieces. So that's what's happening with this one, the unimolecular. It has a form of this, so A breaking into products, and then you can consider all first order reactions are unimolecular. So if it's first order, it tells you that there's some step in there that's unimolecular. And we'll talk about what the steps mean in a second. Bimolecular means that two particles have to collide with two particular particles to collide with each other in order for the reaction to happen. So it's not enough just for something to bang around, hit the solvent particles. It actually has to hit something else, and it's going to react with that something else. You take the form of like two of the same particles having to collide. So the difference between unimolecular and bimolecular is, notice here in the bimolecular, you have to have two A's collide with each other for the reaction to happen. Instead of just any A hitting anything, it has to have two A's collide. Or it can have an AB type reaction where two different things collide, forming the products. Second order reactions are bimolecular nature. That's what makes them a second order reaction, is because there's some part of them that's bimolecular that's important. Now, molecular is really unusual. It requires the simultaneous collision of three particles. So if you can imagine three specific things having to collide together in the right orientation at the exact same time, that event is highly unlikely. So termolecular are really unusual. And anything higher than termolecular would be considered like, unicorns and leprechauns and, I don't know, pots of gold. It doesn't happen in the world. It's just too unusual for it to be a viable mechanism for any kind of reaction that's, happening at real time. So what does molecularity tell us about? The idea here is that when a chemical reaction happens, what we write as a chemical reaction is a summary of what we put in, the reactants, and what we see come out over time, which are the products. We don't know actually what happens. We can't see what happens in between the reactants and products, or they bang around and do several steps and rearrange several times before getting to the products, or if it's just one simple clean thing. The way we gather information about how it happens, though, is we use kinetics and order and molecularity. Now, in these steps, if a reaction is made up of multiple intermediate steps, the slowest of those steps is what we call the rate determining step, because it determines how fast the reaction happens. So you can imagine it this way. You're on a race, a team race, where your team isn't done until all four of your members of your team cross the finish line. So in that situation, you can imagine that it's not the fastest person. It's not that you have the fastest person in your team that makes you win the race. It's that the slowest person is the fastest of the slowest people. And that person will be called the rate determining step. You can't actually do anything until that person finishes, and that determines how fast the reaction happens, not necessarily the fastest step. So as we look at these reaction mechanisms, we're really going to focus in on that rate determining, that slow step, to see what it looks like, and that'll help us understand things better. Before, we can use the reaction order and molecularity to help us figure out, one, if there are intermediate steps, and if there are intermediate steps, what those steps look like. And we'll run through an example real quick. When we consider this reaction below, we had considered this reaction before, and this is basically nitrogen dioxide reacting with carbon monoxide, and it looks just from the equation that this carbon dioxide is just ripping one of these two oxygens off of here and taking it for itself. And if that was the case, we would say, okay, so if this one's colliding with this one, pulling off an oxygen, that means the concentration of this one will be important, and the concentration of this one will be important. And overall, this should be a second-order reaction, bimolecular, right? These two things colliding. But when we find the actual rate law, we see that the rate law is zero order with respect to CO. So it's zero order here, and it's second order here. And that's like, wow, that's really bizarre. We wouldn't have expected that. That's the first thing that'll tell us that, hey, this rate law is telling us that something other than this collision is happening. So let's figure out what that might be. I got ahead of myself, sorry. So seeing that the rate law does not match our mental mechanism of these two things colliding, then we must know that there must be more than one step here. So this is not happening just in one quick step like this. There's other steps going on. And it's bimolecular respect to NO2. We've got to find a reaction mechanism that allows for this rate law that says, hey, this is what's happening. So here's how we do that. Again, that equation, and at first we thought it was this, right? So the oxygen getting ripped. We've debunked that because we're, hey, this isn't in our rate law, and it should be if it's part of the collision that makes this happen. And then this one should be first order. This one should be first order, but it's not. It's second order. And we wouldn't expect second order respect to NO2 because there's only one of them here. So we know as we start developing a mechanism, we need the slow step, because remember the slow step is going to determine our rate. The slow step is going to involve a collision between two NO2s to make it bimolecular. So let's take a look at what that might look like. So we know that here for, let's say, step 1, that we have NO2 plus NO2. That would give us the bimolecularity, the second order with respect to NO2. And that's going to give us something new. And this is where we start using some chemical intuition. So what's going to happen here is this is going to be NO3 plus NO. So there's going to be this transfer of an oxygen from one of the NO2s to the other. And this is just happening with random smacking collisions. I'm going to end up knocking an oxygen off just by accident. Now that's step 1. Now that's great because now we have a rate law or a step in the equation that's consistent with the rate law. It's bimolecular with respect to NO2. And that means that this step must also be the slow step because it's the slow step in the reaction that's going to determine the actual overall rate law. That must be this one. Now we have some problems here. We've created a product that doesn't exist in our reaction. So what we know right now is this NO3 has got to get used up in the next reaction. This guy's got to get used up because it's not part of the actual products. The other thing we notice is that we're missing a CO. So we have no CO yet. So this CO will have to be a reactant in the next equation as well. It becomes important there. And the final thing we notice is that right now we have 2 NO2s. We need to have 1. So we used up 2 NO2s to get here. We're going to have to then produce another one over here to make up for the 2 we lost so that we only actually use 1. So it's consistent with this equation. So let's do it. So we know we got to get rid of NO3. So it goes here, right? And then we know we got to have a CO in here. So we got to put that one in here. And now the question is, well, what could that possibly produce? Oh, well, look at this NO3 has this extra oxygen. So what if it becomes NO2 and then CO grabs it and becomes carbon dioxide. Now it's starting to look really consistent with up here. And as long as this step is fast, it won't affect our rate law. So from the rate law, we know that this step has to be slow and this step has to be fast. So all of that just from this rate law and taking a closer look at the reaction. Now the final step has to be 2 things have to be satisfied to make this a possible mechanism. First of all, there has to be a step, and step 1 here, there has to be a step in which the rate law, the slow step, is consistent with the rate law. This slow step would depend only on the concentration of NO2, and it would do so with a bimolecular collision giving us a second order reaction. Now the next step would be, the rest of the steps are fine to be whatever they need to be to make the reaction work because they're all fast. They won't mess with the rate law. So this next step has to use up all the extra products we created and balance the equation. So to do that, we have to say, okay, let's balance this thing out. Let's add these two equations, see if we get our starting equation. So anything on the same opposite sides cancel, NO3, NO3. And then what we're left with is NO2 plus CO gives NO, nitrogen monoxide, plus carbon dioxide. And we're like, wow, that's consistent with up here. This is a possible mechanism. This step is totally consistent with the rate law. This step is the same added together. When we add the steps together, we get the same outcome as our overall chemical equation. So this reaction is happening in two steps, just like this. And we got that from the rate law. Now, you won't have to be able to figure this out on your own. That's beyond the scope of our course this year. But what you will have to do is, if you're given rate law, or sorry, elementary steps here, these little steps in between, you have to evaluate whether they're consistent with the rate law and whether adding them together gives you the overall reaction. If those two things are true, it's a viable mechanism. All right, that's it for us today. We'll do a little more practice on this. Have a good day, my friends.